to be here once again. Welcome for today's presentation. Today I will go a bit more into glacier and snow hydrology. We have done some basic hydrology on day one, and then we went to some data assessment things and simple hydrological modeling. But today it's a bit different because we are going to discuss snow and glacier hydrology. So what we are going to do in this session, we will discuss why snow and glaciers are important in the Upper Indus Basin, and what are different sources of snow and glacier, how we can get those data sets, from where those data sets can be derived, and what are the constraints in different data sets if someone wants to use glaciers and snow data sets. Again, what we will do is kind of simple rectification. If there are data constraints, which data set is most likely the best available, and how can we rectify the available constraints in the data sets. And at the end, there will be a question and answer session. The Upper Indus Basin, or the whole Indus Basin, is originating from the Himalayas, Karakoram and Hindu Kush region. So Karakoram is over here. So this Hunza and Shigar and Shog rivers are originating basically from the Karakoram range, whereas the Gilgit is originating from the Hindu Kush. Same for the Chitrals and for the Swat river. Whereas the Pamung, or the main Indus, is originating from the western Himalayas, and this is the small one is Astor River. This is also originating from the Himalayas, and these three mountain ranges consist some of the world's largest glaciers. And so overall, snow and glacier will contribute about more than 80% of flow annually. And that's why it's really vital to study snow and glacier hydrology if we are focusing on the Upper Indus or the whole Indus Basin. And why it is important for the future climate change? Because if there is any change in temperature, of course that will increase the melt process, and the glacier contribution to flows may also raise. But it really matters that when this temperature rise is happening. For example, if there is temperature rise in spring and early summer months, but decline in temperature in summer months, so what will happen? There will be increase in spring and early winter and spring months, the flow will rise, but during summer months, flow will decline. And that will change the reservoir oppression and the policy making and the irrigation practices onwards. Yeah, that's what we are going to discuss actually. How global warming is influencing the Karakoram Hindu Kush Himalayas. There are different views of researchers. In the Karakoram range, researchers are saying, or the data is showing that most of the temperatures, like during summer months, particularly in the Hunza and in the Shigar Basin, temperatures are declining rather than rising. But in the other basins, it's rising. So what is happening? Here is kind of positive mass balance. The glaciers are thickening in the Karakoram, but losing mass in the Himalayas and Hindu Kush region. There are quite a lot of glacial lakes. And what is glacial lake? At the end of each glacier, it has a tongue, and a lake can be formed. So there are a lot of lakes, glacial lakes, and what can happen if there is more melt and there is more liquid precipitation, so that pond can be overtopped by water and they can breach, and the flood produced by those glaciers or lakes, this is known as glacial lake outburst flood, and that could be really devastating for small hydropowers sometimes, but for the large hydropowers in in particular, those are really drastic and could be really harmful. So like the glacier study, like the state of the glacier, whether it's thickening or thinning, it's really important, not only for the water resources, but for such threats as well. What is happening? As I said, temperature overall is rising. It's very well understood. Mutually agreed by different researchers. And it is expected that in the Hindu-Kush-Karakoram Himalayas region, the temperature will rise by 2 degrees centigrade by 2021 to 2050. And if this much temperature is raised, so what will happen? Whether the flows will increase or decrease, if glacier melt, what will happen? So that is also one of the reasons that we should study the glacier hydrology. How many glaciers are there? There are more than 10,000 glaciers, small and large glaciers in the Himalayas Karakoram, which are potentially having more than 12,000 cubic kilometer of water, fresh water. And the coverage for the whole Himalayas Karakoram, I'm not talking about the upper Indus Basin. For the whole Himalayas Karakoram, the coverage is about 33,000 square kilometer. There are different opinions from researchers with like the well-known journal published research. There are different opinions for the Himalayas and Karakoram. In the Karakoram, they are saying that glaciers are surging. What is a surge glacier? If I sketch a simple glacier, so this is the terminus of glacier, and this is main body of the glacier. So if this terminus is like expanding, so this is known as surging glacier. But if this is like reducing, so that is known as retreating glacier. So there are these two kind of glaciers in different parts of the Himalayas Karakoram. I would like to show you a flicker prepared by one of the scientists. What they have done, they have used different Landsat images. This is basically the Karakoram region, and what they are saying that glaciers are expanding. You can see a surge over here, a surge over here. You can clearly see surging glacier over here, and similarly here. So what is happening during the last 2 decades in the Karakoram region? Glaciers are expanding, and according to the altimetric data, those are thickening actually. So if there is thickening occurring, so if there is thickening, so what is happening? There is low melt production from the glacier because the density is low. So the surface is covered by seasonal snowfall. So it is producing less water, and the flows are declining due to its thickening process. In the other region, this is somewhere in the Shigar basin, which I have shown you in the figure. Yeah, if there is increase in snowfall and decline in temperature, so what will happen? There will be less melt than snowfall, and that's why there is thickening process. But if there is less snowfall than melt, so there will be negative amount.
This is one big thing. What would be its effects?
What will be the effect?
What will be the side outcomes of that particular process?
Okay, yeah, I can show you a bit over here. Maybe I could explain it more clearly. You can see clean ice over here, which is dark color. So what is happening with passage of time? It is covering with the light one, which is snowfall, which is seasonal snow. So what is happening, if you remember, I have talked about degree day factor or melt factor yesterday, and snow has less degree day factor compared to ice. So this ice is covering by snow, and that's why the melt is reduced with passage of time, and the flows are declining in such basins. Yeah, with temperature, if we are using temperature-based model. But if we are not using temperature-based model, then what we have to do, we have to take radiation and other factors into account if we are using fully energy balance model. But to let the audience know, the basic theme is melt rate actually. So just to be like just for an introduction, that what is a melt rate and how it works.
What is the time interval between these images?
What are you saying, sir?
What is the time interval between these images?
Oh, this is actually you can see it's a published paper in the crash fair, and the time interval is not uniform. It is from 1980s to 2013, and it's not on annual basis or not for each year. So sometimes it's from one image is from 1980, the other would be sometimes could be from 1988, the other one from 1992, the other one could be from 1998. So there is no fixed interval, and there could be like some uncertainty in this analysis, and I will discuss such things in the next slide. So this analysis could also be biased up to some extent, not solely. So these images was from this small Shigar basin, which is in the central Karakoram. But in the eastern Karakoram, which is over here, which is Shiok River, and this Shiok River, one part is known as Nubra, the other one is the Nubra River is actually originating from Siachen, well-known Siachen glacier. And what is happening at Siachen? So if you look at different temporal images from landscape, so one can clearly see, if we look at for the June, for July, and for the August month, so what is happening with passage of time from for example, if you look at this one, the June one, so from 1976, what is happening, this is if this is the reference point, the terminus is shrinking, and according to some researchers, there is about 17%, whole of the glacier loss is 17% of total mass. But according to other researchers, what they are saying that this Siachen glacier and the glaciers in the eastern Karakoram are also gaining mass, because what they are saying that it is very local. This retreat is very local, but in the higher altitude there is gaining of mass, and one shouldn't only rely on the retreat or expansion of the terminus. Again, we will discuss slightly the snow thing, and then we will come what are the constraints in the snow products and what are the constraints in the glacier products. Almost more than if you look at the peak month where snow is maximum, it is about 70%. It is covering about 70% of the total upper Indus Basin, and reduces in the summer months up to about 10%. And this 10%, about 10% is actually the glaciarized area. And if we look at the plot of flow, so one can clearly see that peak is occurring during August and July sometime. So and the precipitation. So there are two peaks. One is in winter, the other one is in monsoon period, which is July-August period. So this July-August precipitation in the form of rainfall is contributing to flow, but mainly the glaciarized portion is producing water to flow. So overall, annually, different watersheds are contributing about more than 80% of snow and glacier melt. This is another plot, and what it portrays actually, if the peak is occurring, it's a general rule of thumb. If a basin has low altitude and its peak is occurring during May or June, so what is happening? Most of the flow is coming from seasonal snow. But if the peak is occurring during July and August, so what does it mean? That most of the flow is occurring due to melt of glaciers. This is a schematic diagram how precipitation is rising with respect to altitude. If we consider this is a mountain, for example, so at low altitude we are getting very low precipitation in this upper Indus Basin, but with respect to altitude, as altitude rises, the peak of precipitation is also occurring at about between 5,000 to 6,000 meters. But afterwards, what is happening due to orographic effect? It produces maximum precipitation at a certain altitude, and then again it starts declining because the air mass is losing a lot of its moisture on the way, and then again there would be a decline. So that's why peak is occurring somewhere in between. If we look at the melt, low altitude have low precipitation and low snowfall, so that is producing less melt. But the melt from the middle altitudes is more than higher altitudes. And why it is occurring? Because most of the time temperature remains in this zone, not at very high altitude. Sometimes like above 5,500 meters, still in summer, it will be below 0 degrees Celsius and there will be less or negligible melt. So there would be melt, of course, and that melt would be just because of the radiation effect. What would happen if climate is warming? So what will happen? The glaciers or the snow cover will turn into ice and will produce more melt. But with passage of time, that melt production will decline. And that's why researchers or the climatologists are worrying that if the glacier melt contribution is enormous in a basin, so it's really vital to study those particular basins that if glaciers are receding, those are losing mass, and climate will warm more and more. So at the end, what will happen that the flow will start declining trend, and there will be adverse effect on water sources as well as hydropower generation and agricultural growth. Well, it's a schematic for the HKH based on different studies, in-situ observations. So I have developed this figure based on different studies who did in-situ observations and based on the climatic stations data. So
warming effect would be a shift in the altitude.
yeah, of course. If we look at this general schematic of a glacier, so what happens if this is the 0 degree centigrade temperature during summer, for example July or August. So what will happen if there is warming effect? So this 0 degree centigrade isotherm will shift towards the higher altitudes, and this whole region will be under ablation. So there will be more melt production at the end. But if there is cooling effect, so this will come downwards, and there will be less melt. In general, a glacier, there is two parts. One is known as ablation zone, and the other one is known as accumulation zone. And what is ablation zone? If we subtract or if we compare snowfall to the melt, and if melt is greater than the outside source of snowfall, for example, then that zone is known as ablation zone. And if this is other way around, if snowfall is greater than the melt, then that zone is in particular known as accumulation zone. It's not only the snowfall actually. There would be avalanches, there would be wind distribution of snow, and there would be vessel movement of snow and ice from high altitude to lower altitude. So overall, the mass balance, if mass balance is negative, the zone is known as ablation zone. If mass balance is positive, the zone is accumulation zone. Yeah, that is a really different thing, of course. Normally, in general, snow is measured as a volume, and that volume is converted into water equivalent. And the water equivalent between snow and water is 1:10. So 10 parts of snow that is equal to 1 part of water. And it really depends on the density of snow. If it is fresh snow, it will have different density. It will have those snow will have less density, and the amount of snow will produce less melt. If there is compact snow, which is ice in fact, so that will produce more melt for the same temperature and due to the density. How we can measure snow? We can measure the snow manually. If we go to the field, we take a pit and we measure the snow, and that's how snow was measured in the field. Like one of our colleagues asked that why it's 2/3 in the winter and 1/3 in the summer, because researchers went to the field, they dug a pit, and they did the analysis how much snow was there during winter, how much is there during summer, and that is one of the methods of measuring snow. We can measure snow with the gauging station. Here are special gauging stations for the snow, but the most like uncertainty is produced by wind. If we are measuring snow at high altitude, it is more likely that the snow accumulation in a band could be affected by wind effect. So, and here are also kind of automated measurements. We can produce measurement by installing weather station, which provide us the automatic reading. So this much snowfall occurred during a particular month, for example. The other method is remote sensing, but remote sensing doesn't provide us the snow pack, like the depth of snow. It only provides us the coverage. And for example, we have seen those Landsat images. In Landsat image, we can see that how much area is covered by snow or ice or the glacier. Similarly, we have I've shown you the modest data where I've shown this monthly distribution of snow. So that is also kind of a measurement method, but we are only restricting those measurement to the area, not to the snow bed. Here are different glaciers. For example, I'm showing only 4. DCW is a digital chart of the world, which was initially used for the glaciarized area. That okay, this much area is in the Himalayas Karakoram, this much area is in the US, for example, this much area is in the Europe. So this was the very first kind of inventory, but the main focus of this study, DCW charts, was not to measure the glaciarized area, and their data was not accumulated or acquired for the peak ablation period, and that's why they had a lot of seasonal snow in their images. One can clearly see, like for example, over here, if we compare this one portion to this one can clearly see that in digital chart of the world, there is more glacier or more snow in their product. And another product is known as LIMS, and RGI is Randolph Glacier Inventory. So one can clearly see there is like especially there is differences in different glacier inventories, and which inventory is right or wrong one has to do further analysis. We will discuss slightly how we can compare and how can we analyze those. MODICE is actually a product of MODIS data, which is snow cover data. And MODICE is providing us the annual minimum snow cover. And they are assuming that minimum snow cover can be considered as glacier area. And what are the pros and cons of MODICE, for example? We will discuss those as well. If we look at the estimate, yeah, of course, one cannot measure like 33,000 square kilometer even in the HKH region, for example. So purely glacier areas are based on the remote sensing data sets, landscape, aster images. It's not very possible. In some areas, researchers are doing aerial photography and they validate the result of remote sensing. So it's also a method of remote sensing, but they are validating the landscape images and aster images with the help of photography. But local measurements, it's really hard to like, particularly in the HKH, because for example, K2 is here, Everest is here in the HKH region, so it's really hard to delineate or to draw how much is the glacier area. So most of the researchers are relying on remote sensing products. And that's why, if we compare, for example, different product estimates, for example, for a source, it is ranging from 190 square kilometer to 541 square kilometers. So which area, which glacier area is correct? It's a question mark at the end. And if someone was using, for example, in a certain year that glacier area is 541, someone is using 190, then what would be their estimate? For example, this one will say about 2.5 times glacier melt. I'm just like projecting, it's not an estimate, I'm just guessing that the estimate could be about 2.5 times of this estimate. So it really matters how much is the glacier area. And if it is underestimated, one should rectify, one should reinstate the glacier as area. If it is overestimated, one should exempt those overestimation. And that's why what is happening, there are different estimates of glacier melt. For example, if we look at Hunza Basin, the estimates are ranging from 23% of annual glacier melt to 80% or 81%. So who is correct, and what are the bases of such huge uncertainty or variability? And if we look at Astor Basin again, the glacier melt contribution is ranging between 19 to 63%. And then if it is 63%, for example, and there is slight rise in temperature, what will happen? There will be significant rise in total volume of annual flow. But if it is 19%, the same temperature will raise overall annual flow very little, like could be about 1 or 2% compared to maybe 15 to 20% rise. So it's really vital to precisely estimate what is the contribution of glacier melt. And for that, one should rectify their glacier and snow products. This is the data of MODIS data or MODICE data. You see, it is not in here, but you can see this is the terminus of the glacier, and there is nothing in this image of MODICE data. And why it is happening? Because most of the termini in the HKH region are covered by debris, and those debris are not captured by MODIS satellite, and that is classified as bare soil. So what is happening? I can show you. If we look at the landscape image, so one can clearly see there is seasonal snow, there is ice, one can distinguish from the colors. And this is the debris covered ice. And what is debris? In fact, snow is sometimes it is coming from slopes of the mountains, so it gets some of the debris with it, and that covers its surface. Sometimes there could be sandstorms, and those produce like those rain, those debris to the side. So that's why most of the termini are covered by debris, and those debris covered portion is actually not captured by modest or modized data. So if we reinstate, for example, those debris covered ice, if we delineate from Landsat image, and that delineation can be done, like the perfect delineation can be done by manual drawing. If we do it automated, there would be a lot of uncertainty, but still it would be something better than nothing. So if we do the delineation and reinstate, one can clearly see all of the debris covered ice were not present in the modized or modest data. So what we should do, we should reinstate those debris covered ice in different time intervals. There could be no debris covered exposure during winter months because all of the surface would be covered by seasonal snowfall. But during summer months, it's really vital to consider those debris covered. We will discuss how much could be the contribution of debris covered ice and if we model the flows. The other constant of modized data sets, if we look at smaller glaciers and smaller patches of ice. So if we zoom in this area and zoom in more, so one can clearly see there are small patches of snow or ice, or could be small glaciers in Landsat images, but one cannot see any green or red dot within this whole picture or photo. There are two dots over here. One can maybe can see those, and those are actually modest data and modized data. So what is happening? Actually, modest and modized data are not capturing small glaciers and ice areas. So what we should do, we should reinstate those small glaciers and areas wherever possible. But of course, one should use best available glacier inventory for that. We will discuss it in a bit, which data is good or bad. Yeah, one should do the initial analysis manually, but it could be automated by using RGS. It can be done automatically. One can what no, those products have their own limitations. So, and that's what's the main theme of today's presentation, that one shouldn't use raw data and shouldn't rely on raw data. They should do the rectification before using it in hydrological modeling, for example. Because it is one of the main limitations of those data sets, and what they did, they have done their kind of validation for the larger glacier areas, and their quality was good. It was within plus minus 10%. So yeah, but if there are smaller glaciers, they didn't do this analysis. It's something new for them, even that okay, their product is ignoring this much of area in the HKH, for example. Yeah, and which basins are vital? Then, in particular, those basins where small glaciers are abundant, and small glaciers are abundant in the Hindu Kush and in the Himalayas. In the Karakoram, there are huge glaciers, and this uncertainty is very less. So it's really matter in the Hindu Kush and Himalayas, not in the Karakoram. So, for example, it was an example for the Gilgit Basin. It is an example of Astor. I'm not going into the detail again, so you can see the slides. It was the reason of underestimation in the hormone. And what is the source of these products? Are glacier inventories. Mainly, those glacier inventories are derived from Landsat images, from ESTER data, and sometimes from the aerial topography. But unfortunately, what is happening, most of, for example, if we look at the Landsat images, one can clearly see that there are kind of a huge amount of Landsat data required even for the upper Indus Basin. More than, I think, more than 17 images are there. And the constraint of Landsat images, those are not available for the same day of the year for the entire region. So one should rely, for example, sometimes an image would be, for example, over here, this image could be from 1998, the other would be from 2000, the other would be from 2001 and 2002. And it really matters, like, because there would be more snowfall, for example, in 1999 compared to 2000 or 2002. There would be more seasonal snow available in a particular year, but what we are doing, we have to compromise, and what we are doing, we digitize this whole of the area and we determine, okay, this is the overall glacier area in the upper Indus or in the other regions of the world. And that's why, if we look at many different products, one can clearly see a huge difference for each and every basin. And for the smaller or the Hindu Kush and Himalaya basins, the variation is huge. It's from 490 square kilometer to 1414 in the Gilgit, and similarly in the Hunza, it's in between 2700 to 5300 square kilometer. And it really depends who is selecting which data and whether their data is correct or the best available. It needs further investigation. So similarly, it's in all basins. It's not in a particular basin. So if we take an example again of a store, it's ranging between 147 to 541 square kilometer, and then it really becomes a question mark that, okay, if there is such difference, whether this 147 is correct or this 541. And the answer is, or the initial answer for the time being is, Modi's data is underestimating small glaciers and it's not capturing recovered ice. So that is one of the factors that, okay, this data is underestimating. Similarly, digital chart of the world is underestimating small glaciers. It is not capturing any recovered ice. And if we reinstate those, so what will happen? It will somehow come to the second or third best available, maybe. But those are the things one should rectify and see how much change will occur if we rectify those. But what is about this 541, whether this is correct? Answer is no. Because they have used a Landsat image where there was a lot of seasonal snow. For example, these boundaries, the blue one is from the Glenn's data, the red one is from the RGI. And this is part of the Astor Basin. And if we look at this image, which has been obtained in 2001, we can see a lot of snow over here, but there is nothing over here in reality. So what they did, they have analyzed an image, a Landsat image for a particular year where there was a lot of seasonal snow. And if someone is comparing these 2 years, they are saying, oh, here is a lot of glacier shrinkage. But whether it's true, they should go for another year from 2013. If they look at 2014, oh, again, here is seasonal snow. So it's not part of the glacier which is expanding or shrinking. It's the seasonal snow during different years.
That's like a year.
Actually, no. In reality, it's no. But one should compare at least for the same months to see the difference. And as I said, Landsat images are not available for the same day or same month for each year. And that's why, for a compromise, what we did, we compared all the images for the same month at least. and that's how the difference can be seen. If I took one image for July and another for September, no one will believe me. They will say, okay, in July there could be a lot of seasonal snow, which is still going to be melted in August or September. Similarly, if we look at the smaller portion of glacier digitized in RGI, one can clearly see there was no glacier or snow available in 2013, for example, when there was less snowfall during the year. And those are not shrinking glaciers in reality, because there is again snow cover available during 2014. So one of the artifacts is actually the limitation of availability of Landsat data. So if Landsat data is available for each and every year and for the same time period, for example for August, then the quality of could be improved. Yeah.
The revisit time of Landsat is 16 days. And while you are saying that Landsat data is not available for every year or every month.
Yeah, but
the basic reason is behind this the cloud coverage.
There are different things which are the constraints. Actually, for the same temporal resolution, you cannot find for the 16-day interval for the same place. You cannot find. If you search for from the Earth Explorer, you will not be able to find for the 16-day interval.
You can download from Globus USGS website after every 16 days data.
Yeah, but one could share those data sets with me as well. So if they find for the 16-day interval for the same part of the edge gauge in particular,
if after 16 days there is a cloud coverage, how can
that will become useless at the end.
It's not the limitation of Landsat, it's the limitation of remote sensing.
There is another limitation of Landsat as well, which is the stripping. There was stripping in different images during 2003 onwards.
Stripping is only in Landsat ETM, ETM plus.
Yeah, of course.
Now, before ETM and after ETM, there is no stripping.
So that's what happened. Like if there was Landsat available for each and every part of the Himalayas Karakoram, the researchers from different institutes should have used those data sets, and one should use those data sets in particular to improve the glacier inventories if there are products available. And of course, the other limitation of Landsat is, as my colleague is saying, that it is also the cloud cover. If there is more cloud cover, one cannot use it for the glacier inventory, because there would be a lot of portion of a watershed or a basin or entire region to be covered by cloud. So that cannot be captured whether there is a glacier beneath that cloud or not. So that is also one of the limitations. And of course, we would go again and again and we'll see how much can we improve our products. Another thing in RGI, for example, there is the latest RGI data. The other one was from 2014. The latest RGI 5 has been published or made available publicly during 2015, December 2015. And if we compare both RGI data, so what is happening? Here is a shift between two data sets. And why this shift is there? Because of the projection. They have used different projections. In RGI data, there was a different projection. In RGI 5, there is a different projection. And in RGI 5 in particular, the projection is correct, by the way. And a lot of small glaciers were merged in RGI 4, but those are splitted in RGI 5. So they have improved the glacier inventory. But still, there is room of more improvement, because if you look at Landsat image, so one can clearly see some of the portion of slope still need more rectification, but it's really extensive work to be done, because most of the work should be done manually, so those corrections need to be done. But still, RGI 5 is slightly improved compared to RGI 4. And according to our analysis, glimpse data is much better than even RGI 5. Another discrepancy, like for example, Easimode produced one of the data sets in 2001, which has been used by different researchers in IMI and other organizations. And they were saying, for example, in the Astor Basin, they were quoting that glaciers are about 605 square kilometers. And what happened? They have used a different projection, and they delineated their boundary, the red spots are glaciers outside of the boundary. So they delineated their boundary based on the Landsat image, and that produced an error in their delineation because it was not appropriately done. And they have quoted, okay, this much area is in the Astor, and in Hunza it's more prominent that most of the glacier area is outside of the basin boundary. They quoted it, and later on, Amy and other researchers used or compared different time periods glacier inventory, and they said, okay, what is happening in so-and-so year, for example, in 1990s, the glacier area in the Astor Basin was 605 square kilometers, but that shrunk to 250 in 2010. But it's not the reality.
I know the basic reason, because this Hunza region is between China and Pakistan. This brown one is from China. So this is the political reason why they have not included this portion of Hunza Basin.
Yeah, but here is an extra bridge.
Yes, I know. And secondly, about a store, if you are saying that some glaciers is they are included or maybe not included, but they have included in Indus River Basin because on the other side of it there is another basin.
Yeah, but I'm not talking about the entire Indus Basin. What I'm saying, what researchers did, they have captured or they have used the quoted values from different other reports. For example, like in this report from Easimode, what they were quoting, the area within the Astor Basin is 605. And they were comparing with the other inventory in a different year, and in the other inventory they were getting 250 square kilometers. And they were saying, okay, there is about 50% of shrinkage of glacier, which is not true in reality. Because, of course, this is part of the entire Indus or the upper Indus, but I'm particularly saying about a single basin, what was happening or why there was a misconception. I'm not entirely saying that there wouldn't be glacier shrinkage. I'm not against that. But the estimates or the interpretation made by different researchers have biases. So one should interpret or do their analysis very carefully. And that's why, if you look at, for example, again, a store, in some research, the researchers have used 299, and the other ones, they have used 541 square kilometer. And what they were saying, okay, this much contribution from non-renewable glacier melt is coming to the flows. And that's what is vital and what should be considered. And for the same reason, one should do the delineation of or separate the thin ice from snow cover and estimate the melt rate separately and do the analysis more carefully and more precisely. I'm skipping few bits of the presentation because we are short of time at the moment. And if we do this separation, so we will have like debris covered ice and clean ice and snow covered area. And this will produce like more melt from this zone, which is 4,000 to 5,000 meter of a particular basin. Whereas from higher altitudes, again, the melt production will be less from very high altitude. Yeah, it's too cold and there is more snow cover compared to ice. What we should do, we should rectify modest data by extracting or by excluding cloud cover using different filters. We should mask no data set. No data set. If we download raw data of modest, there would be some no data set. We should remove those no data set and using different data sets. For example, Glens inventory, glacier inventory. We can mask cloud cover. We can reinstate small glacier. We can reinstate debris covered ice, and debris covered ice is really complex in nature, because there could be two types of debris covered ice. If cover is too thick, it is providing insulation effect. It is protecting the below ice from melting. But if it is thin, it is absorbing more energy and producing more melt. So one should do like some more detailed analysis that how much debris covered ice is thin debris covered and under 10 debris covered, and how much ice is under thick debris covered. So that is something one should do, and maybe in future. And what can we do at the moment? We can rectify the modest data, and then we can split that modest data by using albedo, which is the reflection of snow and ice. So if we use a threshold of albedo, we can separate modest data into snow and ice. And we can reinstate this debris cover, for example, if we delineate it using Landsat images and using snow or ice velocities, there could be a threshold limit for thick and thin debris cover. If we use those threshold limits, we can split it into thick and thin, and then we can reinstate like this one. Then we can see like there was no debris covered ice or clean ice during January, February, and there was exposure of debris cover in March, and then it was increasing during up till August, and then what was happening, there was also exposure of clean ice. So what we should do this exposure with time, and we should estimate how much water is producing or is produced by ice, how much water is produced by snow, and how much water is produced by rainfall. That's what we should do in reality. And yeah.
Is there a video of the ice and the snow is different?
Yeah, of course. The limit is, and according to the field investigation, if the video is 0.3 or below 0.3, it should be ice. And for higher albedo, it should be snow. So that is the field observation threshold limit. So if we use albedo data and we separate the snow cover data according to the albedo, we can do it quite quickly. So coming quickly to this slide, if we ignore all of the snow and glacier-ice area, so what will happen? About 80% of flow, we can predict about 80% of flow is contributed by snow and glacier if we use different hydrological models. So we can conclude that, okay, this much of portion is coming from snow and glacier melt in different basins, excluding Khartoum, which is more dominated by rainfall. I'm also showing one of the last slides, in particular about the debris covered ice. How much debris covered ice is influencing hydrological modeling? It's really interesting to see. It's not actually influencing a lot if we consider only debris covered ice. About 5 to 10% only. The variation is only 5 to 10%. Even if we ignore only debris covered ice and reinstate the small glaciers, the difference will become more or less. And similarly for the other, like if we reinstate debris covered ice but we ignore the small glaciers, the difference is not significant. But what if we only compare the glacier melt estimate, how much that matters in the overall glacier estimate? It's not about the hydrological modeling difference. It really matters. If we look at the glacier melt estimate, and that will be, if we ignore both debris covered ice and small glacier, the difference would be something more than 25% in some basins. Could be about 40 to 50%, particularly in Astor, because the overall glacier area in the Astor basin is not enormous. And if we ignore debris covered ice and small glacier in Astor, the difference would be quite enormous. The overall glacier estimate will be significantly affected. And it's not vital for the hydrological modeling, but it's vital for the glacier estimates. What happened in the past? These are the field investigations, that how much water is produced per square kilometer, or if we consider the specific runoff. So these are the field investigations from different researchers in the Karakoram, in the central Karakoram in particular. And these are the model results in Shigar and Hunza, for example. And I'm only just focusing on the Astor, for example. If there is 479 square kilometer of area, and someone is saying, okay, there is 63% of melt produced by glaciers annually. So how much would be the specific melt? It's about 5.6 meter, which is quite enormous. If 5.6 meter depletion is occurring every year, then the glacier will vanish quite soon. But it's not the fact, it's an artifact of the modeling, because of they have used underestimated precipitation, they have used biased degree depth factors, for example, and there could be other artifacts in calibration of your model. So this is what happened in the available studies. So one should learn from the available study, and they should improve their own hydrological model. They shouldn't rely by comparing only two Landsat images, and they should do extensive analysis based on temporal data. Like my friend said that, okay, here is Landsat data available for shorter time period. One should look at those data sets and select the cloud-free data sets and do the analysis, compare those data sets, and improve glacier inventories, improve modest snow cover data sets, and improve hydrological modeling. Thank you for listening, and if there is any questions, we are more than happy. That's what I said, that there are very limited data available from the field, and it's really hard to measure fall of the glacier. There are very few glacier surveys available, but those are really limited to check the accuracy of Landsat images. Yeah. Yeah, one can do so. Yeah. The area. Yeah. Yeah, but then again, that is again kind of really difficult for a single year. One shouldn't rely on a single year. One should do it for a longer time period, because in 1 year there could be a lot of snow. So even that matter will. Yeah, of course. Yeah. And that's what the main theme, that there are differences, there are uncertainties in the available data set, and which needs further investigation and rectification. So that's what the main theme of today's presentation. Yeah.
So in the previous slides, you told that the models data is not correct, and in the other slides you said one should use the models data. If there is not corrections or the data is not correct of the model.
What I said actually on a polite note, what I said, modest raw data is not correct or perfect. One should rectify those data sets and then use in the hydrological model. That's what I said. Yes?
You said about not the thickness of the degree that covers the ice can handle impact of glaciers. So is there some sort of enhancement standardization about how thick is thick and what is?
Yeah, there are some laboratory investigations, and in some research they are saying about 3 centimeter thickness. After 3 centimeters, it should be considered as thick, and below 3 centimeters it should be. But the other researchers are saying, okay, it's not 3 centimeters, it's up to 5 centimeters. Above 5 centimeters, it should be thick. Below, it should be considered as dense. So here are like the ranges from 3 to 5 centimeters. and which is a reasonable range. And in the Karakoram, the thickness is sometimes the thickness is more than 1 meter. So 5 centimeters is just nothing.
In one slide, you are talking about the projection transformation.
Yeah.
I want to ask that what two projections they have used in previous data and their new data. What are the projections?
I slightly forgot the projection, but the main reason was the datum. They had used a different datum for their projection, and that was making this shift in the glaciers. I can send you the document, and you can see the projection details in there if you drop me an email. My email is written over here. You can drop me an email, and I will send you the document. I just forgot the projection, but I know there is difference in projections, and it was the reason of the shift. Any other question?
Okay, so let's try this.